Okay, good afternoon all. Okay, in from last few lectures, we are discussing related to the heat treatments on steel, and from that we have completed in the previous lecture annealing and normalizing, and in that we have learned what is the purpose of the annealing, what is the purpose of normalizing, then how the annealing and normalizing process is actually conducted, then its different types of the annealing, and after that we have seen some comparison points between the annealing process and normalizing process. Then we have discussed related to different types along with their common applications, annealing and normalizing. In application point, you can directly write that they are used for improving the machinability, or you can say that to make the material softer. For high carbon steels, you can say that high carbon steel or different alloy steels, or directly you can write the name of few components also, which are made up from the high carbon steels or medium carbon steel or alloy steels. Okay, and then after that we will move forward, and now the next heat treatment process is the now in the today's lecture we are going to discuss related to the two heat treatment processes. The one first will be hardening, and the second is the tempering heat treatment process. Okay, and now this hardening and tempering we will see the point wise. In the first point we will see what is the purpose of the hardening, and after that we will discuss how it is conducted. Then if any types are there, we will discuss the types of the hardening, and we will along with this parallelly we will discuss related to the applications of the hardening process. And in the same way we will going to discuss the tempering, and that we will discuss its purpose. Then after discussing the purpose, then the procedure to carry that tempering process, then if any subtypes are there of tempering, that we will discuss. And after that, along with this discussion of types, procedures and purpose, we will discuss related to their applications also. Now we will start with this hardening heat treatment process. Now, mm, if I am going a little bit faster, you can put the message in the chat box. Okay, or if you are having any query, that also you can put in the chat box. Okay, now the hardening heat treatment process. Now in case of these steels, why the hardening in the word itself, it will you will come to the purpose of this process. Hardening, okay, means to improve the hardening, to do the improve the hardness of that particular material. Here we are going to improve the hardness of the steel. Okay, that will be our first purpose, that is to harden the steel. And this hardening hardening process is done to the maximum level, and in this steel we are achieving this high hardness by doing the one transformation, that is we are going to transform the austenite to the martensite. Okay, as this martensite is having the highest hardness, that we have studied in the transformation product of the austenite. Okay, I will show you that slide. Okay, here we have seen this transformation products. Okay, transformation products of the austenites: pearlite, bainite, martensite. Okay, from these three products, martensite is having the highest hardness. Okay, here I have made here one list is pointed according from bottom to top, from the lower hardness to the highest hardness. Okay, coarse pearlite, fine pearlite, then upper bainite, lower bainite, then tempered martensite and martensite. This martensite will be having highest hardness. Okay, means it will provide you the highest strength, and as martensite is more, automatically ductility will be lesser. Okay, depending on these products only, you will get the properties. As in the previous we have seen that we want to improve the you can say that we want to improve the toughness or you want to improve the ductility. Then in case of that annealing and normalizing, which we have learned in the next previous lecture, in the annealing and normalizing we have our final product obtained is the pearlite. We have transformed the austenite into pearlite to to get the more ductility. Okay, to get the more ductility. Are you getting this point? Whenever you want to improve its properties according to our need, just you have to change their structure or phases. Now in annealing and normalizing, we want to increase the ductility. That's why we have transformed this austenite to the pearlite, because this pearlite is having better ductility and toughness properties as compared to the martensite. And now in this hardening process, we want to improve the hardness. We want to improve the hardness. That's why we are transforming this austenite to the martensite. Austenite will get transformed to the martensite in this process. Okay, as we want to improve more hardness in annealing and normalizing, our final product is the pearlite, and this pearlite will be having more ductility and more toughness. Okay, to make the material soften, we have transformed this austenite to the pearlite, so that that material provides a better machinability also. Now here in the hardening process, we want more hardness. Highest hardness can be achieved by the martensite phase. That's why this austenite will be transformed to the martensite. Now how this transformation is done, that you have to write in the procedure. Okay, this is our first aim, that is to harden the steel. Okay, to harden the steel is our first aim. And this improvement in the hardness of this steel material, that we are going to achieve with one transformation, that is the austenite will get transformed to the martensite. Okay, martensitic, by martensitic transformation of austenite, we are going to achieve the highest hardness of the steel. And automatically this second purpose will be automatically achieved when, as you are hardening the steel, automatically its wear resistance and cutting ability of that steel will get improved. That is the second purpose of our hardening process. Okay, only two purposes are there. First is to improve the hardness, that is to do the hardening of the steel. And second purpose is to increase the wear resistance and cutting ability of the steel. And this is the purpose of conducting the hardening heat treatment process. Now how this hardening heat treatment process will be conducted, that is explained in the next slide. Now here we are having different hardening types. Okay, different hardening types will be there, depending on the whichever cooling rate we have selected. Okay, whichever cooling cycle we have selected, depending on that, different hardening processes will be there. The first hardening method, and more commonly used hardening method, is the conventional hardening method. Okay, this conventional hardening, the first type of the hardening is the conventional hardening. Now this conventional hardening process, as we have seen in the introduction part of the heat treatment process, any heat treatment process will consist of heating cycles. There may be one or more heating cycles and cooling cycles, along with some holding time or holding, or you can say that soaking time or soaking cycles. Now here this conventional hardening process will consist of one heating cycle, then the holding time, and the cooling cycle. Now in the heating cycle, you have to explain related to the heating temperature zone, which temperature zone you are going to select. Now for better understanding, the conventional hardening, its temperature zone or its heating zone will be same as that of the full annealing. Okay, whichever temperature zone you have used. Wait, I will show you that in the diagram here. I think in this diagram it is not visible. I will show you that in this. Okay, this is the diagram. You can clearly see it. Okay, here this is the temperature zone. This line, this inclined line is the A3 temperature line. And this inclined line, please see the movement of the cursor. This inclined line is the ACM temperature line. This is A3 and this is ACM, and this horizontal line is A1. This is the A1 horizontal line. Now here in previous lectures we have discussed related to this full annealing. Okay, this is the full annealing temperature zone. above A3 for hypoeutectoid steels, and above A1 for hypereutectoid steels. This is the temperature zone for full annealing or conventional annealing, you can say that. And for normalizing, above A3 for hypoeutectoid steels and above ACM for hypereutectoid steels. And why these temperature zones are selected in such a way that that part we have discussed in the previous lectures also, with whatever reasons are there that I have explained in the previous lecture. Now here for hardening process, what is the temperature zone? For hardening process, temperature zone will be same as that of the full annealing. Okay, this temperature zone. Here I am moving my cursor here. You can clearly see in these slides. Okay, this is the same temperature zone you can use for the hardening also. That is, this is the 0.8% carbon point. Whenever carbon percentage is less than this 0.8, hypoeutectoid steels will be there. And if carbon percentage is more than this 0.8, hypereutectoid steels will be there. Then for doing the hardening of hypoeutectoid steels, you have to select the temperature. Your heating temperature zone will be above A3, above A3. And for hypereutectoid steels, heating temperature should be above A1, above, this is the A1 temperature line, above A1 by 50 degrees Celsius. Okay, this is the temperature zone for hardening. You have to draw this diagram and you have to show the temperature zone in examinations, or please draw this diagram and try to write, means highlight these zones for different processes. For full annealing and hardening, temperature zone will be same, but in that case we are raising the temperature above this A3 and A1 by, you can say that, here we are going to use the 50 degrees Celsius temperature. Okay, but in that case we just have used by 30 to 50 degrees Celsius in that range. But here compulsory we are going to use the 50 degrees Celsius above this. Okay, heating temperature zone will be this, above this A3 for hypoeutectoid steels and above A1 for hypereutectoid steels by 50 degrees Celsius. You have to heat that steel component. This is the heating temperature zone. And now, the second is the holding time or soaking time. Now, after the, you have to heat the component of steel component in this temperature zone, and for a definite period of time. You have to hold the component at that particular temperature for a definite period of time. That time will be termed as the soaking time or the holding time. Now, what is the purpose of providing this holding time or soaking time? To get the, that means to austenize that steel, means to get the homogeneous austenite phase at that particular temperature. To get homogeneous austenite and to obtain the equalization of the temperature, this soaking or holding will be performed. And after sufficient holding or soaking time, now the third cycle is the cooling cycle. Okay, in this temperature zone we have heated above this A3 and A1 by 50 degrees Celsius, and some soaking time is provided so that the steel component will get austenized. Austenized means austenite phase will be there, and throughout that component equal temperature should be there. After that we are going to do the cooling. Now here in the hardening process you have to cool the component in such a way that, here cooling is very important part. Cooling will be done with very faster cooling rate. Okay, from these higher temperatures component is removed from the furnace. All this heating process will be done in the furnace, and now the component is removed and it is cooled. Okay, now this concept will arise here. This is the critical cooling rate diagram for the steel. Now we are here above this A3 or above A1, above this A3 or above A1 depending on the type of the steel. Now from this region you have to cool that type of that material, that austenized steel. It's cooled to the room temperature. Sometimes you have to cool below room temperature also, depending on the uh, its composition, means depending on the percentage of alloying element and depending on the percentage of the carbon, you have to cool it below room temperature or up to room temperature. and this cooling should be done with a very faster rate without touching this nose. Okay, just you have to do the cooling with the critical cooling rate. This is the critical cooling rate. You have to do the cooling from this range with by following the rate that is the critical cooling rate. Means you have to do the faster cooling. You have to avoid the nose of this curve. This point is termed as nose of this curve, nose of this TTT diagram or IT diagram or C curve or S curve. You have to avoid this nose point and you have to do the faster cooling in this range. You have to avoid this nose, means your cooling rate will come before this. Okay, this is the critical cooling rate, and this is the time with limited minimum time possible. If suppose this point is 10 seconds, then you have to do the cooling with a time consuming 8 seconds, 9 seconds, or 10 seconds. That is the critical cooling rate. And this cooling will be done by using different mediums. You can use the water cooling, air cooling, or oil cooling depending on the type of the steel. Okay, if you are having medium carbon steel, then you can go for water cooling. Suppose if you are having high carbon steels or alloy steels, then you can go for oil or air medium to achieve the critical cooling rate. Okay, faster cooling you have to do. Now here, okay, why this faster cooling is necessary? It will get cleared from this diagram. Now this is the TTT diagram. This is the faster cooling. Okay, if from this point we are cooling it, and you have to avoid this point. This is the nose temperature. Directly from this austenite you will end up with this structure, that is martensite will be formed. Okay, martensite will be formed, and this is explained. Okay, here this is the conventional diagram, conventional hardening diagram. Here, from this temperature zone, we are cooling it by avoiding this nose temperature. We have avoided it, and directly we are getting here. That is the up to room temperature. That is, we will get the martensite here. Structure will be martensite, and this martensite will be having very high hardness, and it will improve the wear resistance and cutting ability of the steel. Now in this diagram, this up to this point only the hardening process will end. Okay, from this heating zone, that is austenized steel, it will be cooled to the room temperature by avoiding this nose temperature. That is, cooling will be done with the faster rate, that is the lesser rate with the critical or faster rate than the critical cooling rate. Okay, critical cooling rate is the temperature, sorry, cooling rate which just touches this nose, and you have to do the faster cooling. Okay, before this point your cooling will be done. This will different cooling rates you can use, and you will end up with the martensite phase here. Okay, at the end martensite will be obtained. Now here, in during this conventional hardening process, we are getting the martensite, and from that 900, approximately from 900 degrees Celsius heating temperature zone, here approximately 900 temperature degree Celsius temperature will be there, and from that we are directly dipping that component in the water, and temperature will get fall to the up to room temperature. Due to this very faster cooling rate, due to this very faster cooling rate, some internal stresses will get developed in the component, and to eliminate that internal stresses, we have to perform one uh, heat treatment process, and that heat treatment process is indicated by this curve. This is the tempering. Okay, this process, this is the next heat treatment process, that is the tempering. Whenever you are doing the conventional hardening process, it must be followed by a tempering process. Okay, up to this point your conventional hardening is the process ends, but to eliminate the internal stresses due to the very fast cooling, we have to perform one tempering process, that is one heating cycle up to a 200 or 100 degrees Celsius temperature zone. It is heated and again it is cooled. Again it is cooled. This is the tempering process to eliminate the internal stresses. Now, this tempering process is having different types depending on the temperature zones that we are going to discuss in the next type of the heat treatment process. But here you have to remember that whenever you are doing the conventional hardening process, it should be followed by a tempering cycle. Okay, this is the tempering cycle, or you can say that this is the low temperature tempering cycle. Okay, component after Martin-Side transformation, that component is again heated in a temperature zone of 100 to 200 degrees Celsius for 1 or 2 hours, and again it is cooled. So it is cooled to the room temperature, so that whichever internal stresses due to the sharp fall in the temperature is created in this component, that will get eliminated during this tempering. Okay, so this is the conventional hardening process. Okay, I will repeat it. This conventional hardening process will be conducted in 3 stages. First is the heating cycle. Now, heating is done above A3 for hypoeutectoid steels, or above A1 temperature for hypereutectoid steels by 50 degrees Celsius. Then, in that temperature zone, sufficient holding or soaking time is provided to obtain the homogeneous austenite and equalization of the temperature, means temperature on the surface of that particular steel component and at the center of that steel component should be same, and throughout that component homogeneous austenite should be there, and whichever steel is achieved here, that will be termed as austenitized steel. Okay, we are achieving here homogeneous austenite, that's why it is termed as austenitized steel. And that austenitized steel from this temperature zone, higher temperature ranges, all these processes, heating cycle and holding time or soaking time, these will be conducted in the furnace itself. And after that, component is taken out from that furnace, and it will directly dip into the water. Okay, directly we are collecting that component from the furnace, and it is directly dipped into the water. And here, why it is done so, that is with here we have to do the cooling to the room temperature or below room temperature with a cooling rate just exceeding the cooling rate, critical cooling rate. Okay, whichever rate we are selecting here for cooling, that rate should be faster than the critical cooling rate. And this critical cooling rate is the rate which just bypasses the nose temperature, or which avoids the nose temperature. And here at the end we will end up with the martensite. Okay, this austenite will get transformed to the martensite, and here this process is diffusionless, no diffusion is occurring here. Okay, so this is the cooling rate selected. It should be faster than the critical cooling rate will be, just it will touch the nose of this IT diagram or TTT diagram. And whichever cooling rate you are selecting, it should exceed or it should be faster than this critical cooling rate. Means it should come toward the left side of this. Okay, at this point, if suppose I have, please see it carefully. This will be your critical cooling rate. Okay, which just touches this nose, that will be critical cooling rate, and your cooling rate should be faster than that. Okay, in this way, conventional hardening is done, and at the end, you will end up with transformation of this austenite to the martensite. And some tempering should be done after this conventional hardening to eliminate some internal stresses by following the low temperature tempering. Okay, low temperature tempering is done to eliminate the internal stresses. At the end here, you will end up with the tempered martensite. Okay, product will be martensite only, tempered martensite. Tempered martensite is having more hardness than pearlite and bainite. Okay, in this way, you will end up with getting the improved hardness, that is hardening of the steel is done, and you will end up with the more better cutting ability and better wear resistance of that steel material. This is the conventional hardening. Okay, please draw this diagram, and if you are having any difficulty, kindly put that in the chat box. Please tell me that whether you are clear related to this conventional hardening process, because next three types here, next This is the one type only, that is conventional hardening. After this, time tension hardening will be there, then os forming, mar tempering. These are some types of the hardening that will just depend on this. Just the cooling curve will be different. Heating cycle and holding time will be same. Just we are changing the cooling process. Depending on the change in the cooling process only, we are having that type of the different hardening will be there. Just we are changing the cooling curve, or we are changing the cooling rate. Okay. If you are having any doubt, please ask me. Or if you are not having any doubt, put that in the chat box, that all points are clear. One Gaudi is there. One Gaudi. One, are you there? Just you're joining the meeting and not listening it. Okay. Pritam Padge is there. Roll number 57. Pritam Padge, are you there? Pranay Disley.
Yes, sir. Yes, sir.
Okay, okay. All points are clear related to this conventional hardening.
Yes, sir. But, sir, can you revise about internal stresses after lower the temperature?
Means after completing.
Martin setting phase.
After this, you have not understood this point, na? Okay.
Yes, sir. Sir.
Okay, I'll repeat it. I will repeat it. Okay, what happens here? During the hardening, we have heated that component in the first step from room temperature to higher temperature range here. Okay, above A1 or above A3. Generally, it will be higher temperature than 700 or 900 degrees Celsius. And after this, after sufficient holding, we are cooling that component from high temperature range directly to the room temperature. Means here approximately 900 degrees Celsius temperature will be there, and it will be cooled directly to the room temperature, suppose 25 or 23 degrees Celsius. Then due to this large temperature change within very short period of time or short time span, what will happen, some due to that change in the temperature, thermal stresses will get created in that component. Okay, some thermal stresses will be there, and due to that thermal stresses, some cracks may get created in that component. Now to avoid this, what we are doing, after cooling it to this room temperature, again we are taking that component and again we are heating it. Again, after completing this cooling process, we are taking that component and heating it to the 100 to 200 degrees Celsius temperature zone, and holding there for 1 to 2 hours, and again it will be cooled. And due to this, what will happen, whichever internal stresses are created due to sharp temperature changes, that will get eliminated here. Okay, means just one more heating and cooling cycle, which is having lesser temperature up to 100 or 200 degrees Celsius, we are doing this. Then due to this, what will happen, internal stresses will get eliminated. Whichever stresses are there due to sharp change in the temperature, that will get eliminated. Okay, is it clear? Hello, Pranay, whether it is clear? Okay, okay. If it is clear, um, okay, Chair, then we will move towards the next type. Okay, just here, I will repeat it again. Due to this cooling cycle with very fast rate, some stresses will get created, that we can say that thermal stresses will be there due to sharp change in the temperature from suppose 700, 800, or 900 degrees Celsius directly to the room temperature. Some stresses will get created in that component. It may produce some cracks. To avoid that, we are again taking that component and heating it to the 100 to 200 degrees Celsius temperature, holding there for 1 or 2 hours and cooling it to the room temperature again. Due to this, that stresses, whichever thermal stresses are there, it will get eliminated. Okay, you can say that this low temperature tempering, or you can say that post heating process also. Okay, but it consists of one cooling cycle. That's why it is termed as low temperature tempering. Okay, and then after this, the next type of the hardening is the interrupted hardening or time quenched hardening. Okay, now in this interrupted hardening or time quenched hardening, the first two cycles, that is the heating cycle and the holding time or soaking time, that 2 points will be as it is, that you can write as it is. That just the cooling cycle here, it will be different. That here we are doing the cooling. Okay, cooling will be done with a cooling rate. It will be more than the critical cooling rate. More than the critical cooling rate means we are avoiding this nose. Cooling will be done with the faster rate. It will come in this point range. Okay, and here the initial cooling will be done with a very faster rate. That is, the initial cooling will be done in the water medium, and after that, when it the temperature reaches just below that nose temperature, we are taking that component out from that water medium, and we are doing the little bit slower cooling, either by using oil medium or air medium. Initially we are using more faster cooling rates with the help of water medium. Water will remove the heat with very faster rate, and after that, when temperature falls below this nose temperature, we are changing the cooling medium. Here little bit slow cooling medium, either oil or you can use the air depending on the type of the steel. Air can be used for the alloy steels. Okay, air can be used for the high carbon steels or alloy steels. So this is the, and at the end you will end up with the martensite. Okay, austenite, here austenite will be there. This austenite will get transformed to the martensite, and during this we are using the two different cooling mediums. Initially faster cooling medium, water medium will be used, and when temperature reaches just below this nose temperature, we are changing the cooling medium to either oil or air. Here, which diagram here I have taken this, this diagram is taken from the VD Kodgire's book, and this diagram is for time quenched hardening of medium carbon steel. Okay, this is for medium carbon steel. Initial cooling is done in the water, and when temperature falls below this nose temperature, the further cooling is done in the water medium, sorry, oil medium, and final product obtained is the martensite, and it will provide you the better hardness. Okay, better hardness. So this is the time quenched hardening or interrupted hardening. Then after this is for this example, whichever water and oil. This is for the medium carbon steels. If suppose you are using the high carbon steels, if you are doing the hardening of the high carbon steels or alloy steels, then your mediums will be, first medium will be oil and then air. Okay, because with little bit slower cooling rates also, in case of high carbon steels or alloy steels, you can do the hardening. Okay, you can do the hardening easily. But this type faster cooling rates are required to form the martensite. Faster cooling rate required to form the martensite in case of the low carbon steels. It cannot be achieved with the help of this water medium also. That's why the low carbon steels are termed as non hardenable steels. Okay, low carbon steels requires the cooling with very faster rate, and that mediums are not available, or you cannot do the cooling with that much faster rate with the help of water solution or brine solution also. That's why low carbon steels are termed as non hardenable steels. Okay, these questions may be asked in the competitive examinations, why the low carbon steels are termed as non-hardenable steels. The reason, very basic reason is this, that is it requires very faster cooling rate, and that rate cannot be achieved with the mediums available like water or brine solution also. Okay, and after this hardening, second type of hardening, the third type of hardening is mar tempering or mar quenching process. The first two steps, that is the heating and the holding time, heating cycle and the holding time will be same. And after that we are going to use the cooling cycle. Now here the cooling will be done in such a way that okay, whichever steel is here at the higher temperatures, it will be termed as austenitized steel, and it is cooled with a cooling rate which is faster than the critical cooling rate. Faster than this, critical cooling rate will be like this, it will just touch the nose and it will come to the room temperature. But faster cooling rate we have to select, and here the faster cooling rate is selected. And when you reaches the temp here in this temperature zone, just below the nose temperature and just above the ms temperature, just above this ms temperature, at this temperature zone temperature is held constant for some definite period of time. But here one care is taken that it is not allowed for binite transformation, means austenite should be there only. That austenite is not allowed to get transformed to the binite, means it should not cross this line. Okay, if it crossed this line, then it will get transformed to the binite. Before this line only it is held for some definite period of time. And then what will happen, due to this constant temperature, the martensite, whole martensite, whichever martensite is forming throughout that component, it will be formed at this particular constant temperature. And at the end you will end up with the martensite only. Here martensite transformation will occur. Okay, and you are then cooling it to the room temperature. Whichever transformation of martensite is occurring throughout that cross section, it will take place at the same time. Here we are getting the martensite. Okay, martensite is transformed, but the tempering of that martensite is done due to the this holding at this temperature for some definite period of time. That's why this process is termed as mar tempering. This mar for martensite, and remaining will be tempering. Okay, is MAR for martensite and tempering. Martensite's tempering is done here. And how it is done? Just below this nose temperature and just above this ms temperature, we are keeping that steel component or holding that steel component at this temperature, constant temperature for definite period of time. Due to it, this it will end up with the tempering of that martensite. And you will, what is the meaning of tempering of martensite? Here martensite will appear granular in nature. Okay, means at the end you will get the tempered martensite. Here you will get the tempered martensite, that is martensite will be present in the granular shape. That's why this process will be termed as mar tempering or mar quenching process. And this quenching is nothing but the cooling process will be done in the air or oil medium, depending on the type of the steel material. Okay, depending on the type of the steel. Now And where it is applicable, now this mar tempering process, it is used or applied only for high carbon steels, or it is applied for low alloy steels. Okay, it is not used for medium carbon steels, or it is not used that, and remaining low carbon steels are non hardenable. Okay, the whichever that time quenched hardening is there, that you can use for medium carbon steels, high carbon steels, and alloy steels also. But this mar tempering process, this can be used when you are having higher percentage of alloying elements and higher carbon percentage. That is, it is used for hardening of high carbon steels and low alloy steels, or you can say that the alloy steels. And here, what are the advantages over the other processes? As we are here, we have kept the temperature constant, the chances of the cracking or chances of the distortion and warping will be very less. Okay, martensite is forming, but as you have held the component at this temperature zone for some definite period of time, chances of cracking, distortion, and warping of that components are very less. This is the advantages of this mar tempering process. Then after this mar tempering process, the next hardening is the os forming process. This is very much similar. Again, os forming is very much similar hardening process as compared to the mar tempering process. As compared to that mar tempering process, this os forming is very much similar, just little bit difference is there. Initial two cycles will be same, that is heating. To perform the hardening process here, we are heating that component, okay, from initial cycle, heating above A3 if it is hypoeutectoid steels, or above A1 if it is hypereutectoid steels by 50 degrees Celsius, then holding at that particular temperature for a definite period of time to get homogeneous austenite and equalization of the temperature. And after that, the cooling is done. This is the cooling cycle. Cooling is done with a faster rate, or rate exceeding the critical cooling rate. Critical cooling rate will be just touching this nose. Now, whichever rate which will come in this left portion, it will be faster rate than the critical cooling rate. And in this cooling cycle, when the temperature falls below this nose temperature and just above this ms temperature, on that component we are taking that component and we are performing one rolling or forging operation on it. And after performing that rolling and forging operation at this temperature zone, it is again cooled. Okay, we are cooling it, and this cooling is generally done in the oil medium. Okay, it is generally done in the oil medium. Then what will happen here, due to this forging operation, here we are performing the forging or rolling operation. What will happen here, this austenite, deformation of the austenite will take place. This AUS stands for austenite, and deformation, that is the forming will occur. That's why this hardening process will be termed as os forming. Austenite, okay, austenite will get deformed. That's why it is termed as austenite forming, due to the forging or rolling operation which is performed just below nose temperature and above this ms temperature. Okay, and again it is cooled with the help of oil medium, then you will get the tensite. Okay, as in between this we have performed here this forging or rolling, this austenite has get, means plastic deformation has occurred there. Due to that, what will happen, whichever martensite is formed here, automatically it will provide you the better tensile strength. And along with that, due to deformed austenite, it will provide you little bit ductility also. Means it will provide you the combination of tensile strength and ductility due to this intermediate operation, and that is rolling or forging intermediate operation performed on that component during this cooling process. That's why it is termed as os forming. Okay, austenite deformation will occur, and it will produce a martensite having combination of tensile strength and ductility. Okay, and this process can be used for high carbon steels and alloy steels. Okay, different components made up of high carbon steels or alloy steels. For that, if you want to do the hardening to improve the hardness with combination of little bit ductility, then you can go for the moss forming process. Moss forming process. Okay, these are just the phases. And whenever you are drawing explaining any process, or if you have draw this diagram, then you have to mention whichever in the symbols you have used. This A stands for austenite, then this is A austenite, M for martensite, M for martensite here, then this A austenite, then ferrite, cementite. These are the A1 and A3 temperatures. E just stands for the uh, you have done the heating, and after that you are doing the cooling. That's why these symbols E is used. Sometimes it will stand for the equilibrium also. Okay, E3, A1, or simply you can write A3 or A1 also. No problem will occur there. Then this ms mf temperature, martensite start, martensite transformation start temperature, martensite transformation finish temperatures. In the similar way, bs bf and then ps pfs will be there for pearlite transformation start and pearlite transformation finish temperatures, and bayonet transformation starts and bayonet transformation finish temperatures. Okay, that here you, and some other heat treatment processes I have taken here. In this diagram, you can see this BSBF, that is binite transformation start and binite transformation finishes temperatures. Sometimes that austenite is mentioned with this gamma phase also. In few diagrams, A symbol is given. Don't get confused. It is same process. Okay, same phase. This is austenite. Sometimes they have written is austenite. A stands for austenite or gamma for austenite. Same phase there. Don't get confused in this. Okay. Now some more heat treatment processes are there that we will finish in this lecture only. Okay. Just the heating time cycle and holding time will be same. Just what is the difference here? The difference will be in the cooling rate. This is the different cooling rate. Now this process is the os tempering process. Okay, os tempering process. Now during this cooling, when temperature falls below this nose temperature and above this ms temperature, in this temperature zone the temperature is kept constant, and here the binite transformation is permitted. Okay, this does not comes in the hardening process. Just the curves are of similar type, that's why I have added that part at the end of this hardening. These are not the types of the hardening. Only four types of the hardenings are there: os forming and mar tempering. These remaining three types I have added here, these two curves and this one. These are not hardening process. These are just heat treatment processes. Depending on our need, we are going to use it, get to change the microstructures or phases. Now here we have kept the temperature constant in this temperature zone, just below nose temperature and above this ms, and we will end up with the formation of the bainite. Either upper bainite is formed or either lower bainite is formed. Okay, upper bainite or lower bainite is formed. Okay, now here this binite will provide you the hardness. Okay, as binite product is the binite, it will provide you the hardness, but it hardness will be little bit on the lower side as compared to the marten side. Then here to do the cooling process it requires more time, as during this here it is taking more time, as here we are permitting the binite transformation. It requires more time, that's why this process is costly. This is very costly process. But whenever some amount of You want some amount of toughness, better toughness as compared to on that marten side, which sometimes may result in the brittleness of that material. Then you can go for this heat treatment process, that is the tempering. It will be termed as the tempering process. Or sometimes you have to remove that retained martensite is there. Retained martensite means at the end, of the cooling, some amount of austenite will remain as it is, which is present here. Some amount of austenite will be there to eliminate that retained austenite. Whenever martensite phase is there, some amount means zero point 0.1 or 1% austenite will be there. To eliminate that retained austenite, we are carrying out this process, and we are forming here bainite instead of forming the martensite, and its hardness is a little bit nearer to the martensite. Then the next two heat treatment processes we are using here, the left hand side diagram is for patenting, and the right hand side diagram is for isoforming. On the screen, left hand side diagram is for patenting, and the right hand side diagram is for isoforming. Now here we are doing the quenching, and now quenching or cooling. During the quenching or cooling process, here we are holding that sample, steel, austenized steel sample, at a temperature zone near to the nose temperature. Near to the nose temperature, it may be little bit higher than nose temperature or little bit lower than the nose temperature. For a longer period of time, for a longer period of time, we are keeping the temperature constant here nearer to the nose temperature. And what will happen after holding, we are cooling it then to the room temperature. Then here the transformation product formed will be perlite. Okay, here we will end up with the transformation product perlite. It may be fine perlite or coarse perlite, or sometimes you may get upper bainite also. You may get here upper bainite also. Now here, as perlite is forming, generally we are getting here perlite. That perlite will provide you the better toughness. Whenever you want to improve the ductility and toughness, you have to go with this patenting process, and the end product will be perlite. Okay, perlite. Sometimes you may end up with the upper bayonet also. And as perlite is there, its toughness will be very high. And these type of processes means whenever you want to perform a wire drawing operation on that component, before performing that wire drawing operation, you are going to perform this patenting heat treatment process. This heat treatment process we are going to perform. After completing this heat treatment process, we are going to perform the wire drawing operation, because now that material, steel material is having more toughness and ductility. Then the next heat treatment cycle is the isoforming heat treatment cycle. Now here heating cycle and holding time will be, processes will be same. That two processes you have to write, and after that you have to add related to this cooling cycle. In that cooling cycle, this austenitized steel will be cooled, and when temperature reaches just above this nose temperature, okay, just above this nose temperature, on that component, when a rolling or forging operation is performed, rolling or forging operation is performed, and after that it is cooled to the room temperature. Here you will get only perlite. Okay, only perlite transformation will occur here. Means this, whichever austenite is there, only perlite you will get, and it will provide you the highest toughness from these two cycles. Suppose this patenting and isoforming heat treatment cycles, isoforming will provide you the better toughness, and it will make that steel material suitable for the further wire drawing operations or different drawing operations. Okay, it will improve the toughness and ductility. These two will be used for improving the toughness and ductility to the highest values. Okay, so in this lecture we have completed this part. What is the uh, why hardening process is conducted, then how the hardening process is conducted with the different stages, that is heating cycle, holding time, and cooling cycle. And how, which type of critical cooling rate you have to select, then why the temperature zones are above A3 for hypoeutectoid steels and above A1 for hypereutectoid steels. And then different types of the hardening: conventional hardening, time quenched hardening, mar tempering, then os forming we have studied. And after that, three different heat treatment cycles. These three will not come under the hardening process. These are the special other heat treatment processes: tempering, then patenting, and isoforming. We have discussed these. uh, if you are not having any query, I will stop here. Or if you are having any query, please ask me or put that in the chat box. I will clear it. I will try to clear it. Okay. Please confirm that all points are clear. Okay, roll number 8. Are you there? Deep Jyoti Sathe. Roll number 8. Please confirm that all points are clear.
Yes,
Okay.
sir.
Then Sachin Shirsagar. Are you there? 42. Roll number 42. Sachin, are you there?
Yes,
Okay,
sir.
okay, okay. Well, all points are clear.
Yes, sir.
Okay, 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 no problem. Then in this way we have completed this points. Means in this lecture we have completed the hardening of the steel. Then in next lecture we will see the. I will stop here. In the next lecture we will see the tempering process for the steel. For now I will stop here. You can move, go with your next session or continue with your next sessions. Thank you. Thank you.